Today our topic is the planar and the dual graph. This is our topic, planar and dual graph. So now, first of all, what is the planar graph or what is a plane graph? So basically planar word comes from the concept that if you can draw a curve in a plane, if it is possible to draw a graph in a plane, then we say that this is a plane graph. And also if in this graph no edges are actually intersecting, then we say that this is one of the planar graph. That means suppose if you consider this graph, let's take this graph. So in this graph you can see this is one of the complete graph with 4 vertices. So this is V1, V2, V3 and V4. These are the 4 vertices of this graph. Now you can see that in this graph it's look like that these two edges are intersecting, but you can draw this graph again in this way, that suppose this is V1, this is V2 and this is V3 and this is okay, there are two V3s are there, so not this is not V3, this is V4, and you can draw this, connect this V1 and V2 also in this way. So now you can see that here if these edges are E1, this edge is E2 and this is E3, E4, this edge is E5 and this is E6, then E1, this is E2, this is E3, E4 and this edge is E5, but we draw this E6 edge in this way. So now you can see that in
ये
this,
इसके ऊपर सर ये इसके ऊपर ओवरलैप कर रहा है क्या? ये
actually
जो
if you can draw the graph in this way that no edges will overlap, then we say that this graph is a planar graph, otherwise not. So if it is possible to draw the graph in this way that the edges will not overlap, then this graph is called a planar graph, otherwise not. That means suppose if I give you one of the graph like this, like the K5 graph with the 5 vertices like this, and suppose then you connect all these 4 vertices with the lines and then with the 2 vertices with the line, and then you will see that it is not possible to make it a planar graph. So you can't draw this graph in a way that 2 point or the 2 edges will not intersected. Just try to do that. So first connect all the line with the remaining vertices like this. So just connect these 4 vertices. After that you want to connect from here to all the other vertices. So let's start connecting that, because you can connect it like this way and you can connect it like this and also you can connect it like this. So this is possible that we connect again these vertices to the every other vertices. So this is our first vertex. So first vertex to we connect the second, third, fourth and the fifth vertex. After that, starting from the second vertex, we connect the third vertex, the fourth vertex and also the fifth vertex in a way that they will not overlap. And after that, what we have to do, we have to draw the curve from the third vertex. So whenever you come from the third vertex, so there is no ways to go without intersecting the lines. Is it possible? You can connect this 4 and 5. It is possible. You can connect this 3 and 4 and you can connect this 4 and 5, but you can connect this 3 and 5 without overlapping any of the edges. Is it possible to do that without overlapping any one of the edges? Is it possible?
No, sir.
No. So
No
that,
sir, it is not possible.
so that means it is not a planar graph. So now you all can understood the what is the planar graph. So a planar graph means a graph G. So if we take a formal definition, the definition looks like, so a graph G is said to be planar, is said to be planar to be planar if it can be drawn, on a plane, and such that no of its edges two of its edges intersect, otherwise G is called non-planar. Otherwise G is called non-planar. Non-planar. Is it clear to everyone? What is the planar and what is the non-planar graph? Now again we are taking 2 or 3 more examples. So this graph is actually a complete graph. So this is a non-planar graph. This graph is a non-planar graph generally. So if we draw this in this way, so this is one of the non-planar graph and it is called K5. So K5 means the complete graph with 5 vertices. So complete graph means a graph where we connect each possible pairs of vertices by an edge. So that's why this is called a complete graph. So here there are 5 vertices and we connect them with every possible vertices, and we have 10 edges here, and this is called K5, and K5 one of the example of non-planar graph. Okay, so now we are taking 1 or 2 more examples of the planar graph. So some more example of planar graph. So suppose if you take this graph, just take this graph. Now tell me, is it a planar graph or not? And how you can make it planar? Is it a planar graph?
No, sir.
Why
স্যার
not?
ইন্টারসেক্ট করাতে হবে তাহলে প্ল্যান
Because sir,
No, no,
edges
no.
यहाँ पे intersect
If
कर रहे हैं,
edges are
एकदम
not
overlap कर रहे
intersecting,
हैं.
then if edges are not
Overlapping, sir.
intersecting, okay. So now we give the vertices. Actually, these points are the vertices. These points are the vertices. So now we are marking the vertices. This is V1. Okay, someone wants to join. Okay, so this is V1. Take that as V2. This is V3. This is V4. This is V5, V6. This is V7. Take it, and V8. Okay. So now tell me that is it a planar or not? Now by looking it, you seems that these lines are intersecting, but you can also take it as a 3D figure. That if it is a 3D cube, then actually these lines are not intersecting, but it actually breaks the planar concept because you can draw this in a plane now. So we have actually 2 requirements. You have to draw the graph in a plane. That means if this graph can be drawn in a plane, and also no 2 of its edges intersect. These 2 are our restriction or the requirement that to be a planar graph. So is it possible to draw a graph? So if you can draw an isomorphic graph, then it is also okay. That corresponding to that, if you can draw an isomorphic graph, isomorphic means just the same graph, just another diagrammatic presentation of the graph. That means a 1-1 mapping between the vertices of these 2 figure. So now we are actually drawing another figure from this set, and in this way, that these are V1, this is V2, and this is V3, and this is V4, and after that we are drawing another this. Now V1 connected with suppose V7, so we draw it by V7, and then another this, suppose this is V4 and this is V8 and V3, so this is take as V6 and take this as V5. Now connect these edges. So now tell me, is that a planar graph? It is just the same presentation of this graph. You can see it.
Yes, sir.
And no edges are intersecting at all. So that means it is possible to make some isomorphic image of this graph in which the edges are not overlapping, and also you can draw it by a plane, because you can see that this is a just plain paper, this is a plain whiteboard, and if we can draw it in this plane, then it is obviously a planar graph. And if you can draw this in this way, that no edges are intersecting actually, so that means these two are example of the planar graph. Again, take another example of such type, just take that, and after that take it and take it. Now join them, and this is v1, v2, v3 and v4. Now tell me, is it a planar graph?
No, sir.
No,
Why?
sir.
Why it is not a planar graph?
Intersect
Yes,
করছে,
sir,
sir.
planar. Planar.
No, no, it
tell
is
me
planar, sir.
na, why it is
It
not
is
a
planar,
planar?
sir.
Obviously,
इसको
because
change कर सकते हैं.
we can make one isomorphic image of this graph by this way. That means these are v3 and v4, and we can pass this line from here to here, na? We can pass this line because this is v1, this is v2, this is v3 and this is v4. So there are two lines, one connecting v2 v4 and another connecting v1 and v3. So we preserve all these edges. That means if this is your e1, this is e2, this is e3 and this is e4 and this is e5, then we preserve all these lines e1, e2, e3 and e4, and we just change this line from here to here, but we preserve all the vertices relation. That means the incidence matrix relation and the adjacency relation. We preserve all the relation. So planar graph means if it is possible to draw a graph in this way, that no edges are intersecting and in a plane you can draw that, then it is a planar graph. That means this is a planar graph. By the first look, you actually guess that this is not a planar graph. You think that it is not a planar graph, but you can draw it in a plane. You can draw an isomorphic graph of this graph. You can draw the isomorphic graph of this graph and also for the first. So that's why these graphs are called the planar graph. Now, is it clear to everyone what is planar graph? Or
হ্যাঁ, স্যার,
Yes,
বুঝতে
sir.
পেরেছি।
Yes, sir.
so now again take another examples, and this is another like the K5 relations or the K5 graph. This is also one popular graph, and this is a graph with 6 vertices, graph with 6 vertices and 9 edges. You can see these are the 3. Okay, this is one intersecting line. This is one intersecting line. So these are v1, v2, v3, v4, v5 and v6. Okay, so and these are the edges e1, e2, e3, e4, e5, e6, e7. It is e8. Take it as, I take it as e9. Now tell me, is it a planar graph or not? Is it possible to make it planar?
Non-planar. No, sir.
Okay, it is a non-planar graph. You can't make it. And this is just like the another isomorphic graph. You can draw an isomorphic graph of this graph like this. Here you can see that degree of each vertex is what? 3, na? Degree of each vertex is 3 unit. You can see that. That with every vertex there are 3 connecting lines. So that's why degree of each vertex is 3. And this is not a vertex. This intersecting point is not a vertex. So you can draw one of the isomorphic graph of this like 1, 2, 3, and here you can take 1, 2, 3 and just join one by one and one to the remaining other 3 lines, one to the remaining other 3 lines in this way. And okay, So here also for this graph, every vertices have a degree 3 and there are connecting 3 lines, and this is also one of the isomorphic graph. This, if you take it as a f of a and if you take this as f of b, then you will see that means f of a means actually figure a. This is actually, if you take this as figure of a and if you take this as figure of b graph, then these two graphs are actually isomorphic graph. So isomorphic graphs are, their incident matrix are same just up to the permutations of the row of the column. That's why this is called a isomorphic graph. So here these two figures are same, their vertices degrees are same, but, and this is one of the popular graph which is called the K33 graph. That means the bipartite graph of 3 vertices. So this is one of the bipartite graph. So bipartite graph means if you can partition your set in these two way, and where the, for every edge one vertices is on the first partition, this first partition, and another is on the second partition vertex. Every edge, that you just take one arbitrary edge and you will see that one edge at this set v1 and another edge is, another vertices is belongs to the this set v2, and there is no connecting edges between the v1 set, no connecting edges. So that's why this is also K33. Now these two are very popular graph, very popular non-planar graph, very popular. The first K5, so first graph is the K5 number 1. What we already says that this graph, that complete graph of 5 vertices, complete graph with 5 vertices, and then we discuss another graph, and which is that K33, and these two graphs have a special name. These are called the Kuratowski graph. This is the spelling Kura and Towskis, Kuratowski's graph, and he first discovered this nature of this graph, and it is called the Kuratowski second graph, and it is actually K33, K3 comma 3, and that means a regular graph. It is a regular graph with 6 vertices and 9 edges, and not only that, it has a special features. It is the non-planar graph with smallest edge. It is the non-planar graph, planar graph with shortest number of edges, number of edges. That means if a graph has 8 edges, 7 edges, 6 edges, then you can make it a planar graph. It is possible to draw. So the first non-planar graph, that means the smallest, with the smallest number of edges, is a 9 edges graph, and this is the K33. And similarly, the first graph, that the minimal graph, non-planar graph, is with the vertices, 5 number of vertices. This K5 is another graph where this is the first non-planar graph with the minimum number of vertex or the vertices. So K5, and this is the figure of the K5. So we already draw this, but again we draw the K5 graph for this importance. So that means if a graph have this type of chart, you can see the previous figure now. This graph have a 1, 2, 3, 4, 5 and 6 number of edges. So you can make it a planar graph. Always it is possible. In this graph you can see it is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8 and 9, 10, 11, 12. So there may be anything. It may be planar or maybe non-planar. That's we have to check. But if in this graph you can see again 1, 2, 3, 4, 5 and 6 number of edges, then obviously it is always a planar graph, because the first non-planar graph is of 9 edges. First non-planar graph is of 9 edges, and for every other graph with less than 9 edges is always a planar graph. And now we comes to the second thing with the vertex. So here there are 1, 2, 3 and 4 vertex. If you take the 3 vertex, then it is always a planar graph. If you take the 2 vertex, it is always a planar graph. Whatever you may try, it is always a planar. If it is a 3 vertex, then whatever you may try, it is always a planar graph. Whatever you may draw this type of line, but it is always a non-planar. It is always a planar graph. But if it is a 4, then again it is also a planar graph. Whatever you may try like this, you may try like any other of this type of pattern, it is always a planar graph. Okay, but if the first regular, if it is not a regular, then one other thing, but the first simple non-planar graph is of what? Vertices. That means first regular graph with the vertex which is 5. So if we state, it looks like the first non-planar graph with the smallest number of vertices is the first non-planar graph with smallest number of vertices is K5 with 5 vertices. This is the first. So K5 is the, and obviously these are all the regular type of graph. These are all regular type of graph. That means degree of the edge vertices will be same, or these are simple graph. That means no loops and no parallel edges are there. And so that's why if it is a simple and regular graph, so the first non-planar graph with the smallest number of vertices is K5, and the first non-planar graph with the smallest number of edges is the Kuratowski second graph. It is the K33, and it is called the Kuratowski first graph. Kuratowski's first graph. So these are just examples of two popular non-planar graphs. And after that, you will see one of the theorem that if any graph contains any one of these Kuratowski's first graph or second graph, it is always a non-planar graph. If your graph contains this type of graph as a subgraph, that this Kuratowski's graph, then you can directly say that your graph is a non-planar graph. So that's why these two graphs are very much important, the Kuratowski first graph and the second graph. So first graph means the K5 graph, this graph, and the second graph means the K33 graph, bipartite graph of 3 vertices, and these have 6 vertices and 9 number of edges. So these are just example. Now now it comes to another important thing which is called the region. What is region? Is there anyone who can say that? What is region? What do you think by region term? Now just take one planar graph, one very simple planar graph. Am I audible to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So now take this planar graph. So there are total number of 4 vertex. So 4 vertices, 1, 2, this is 3, and this is 4 number of vertices. So number of vertices, it is generally denoted by n. Here n is equal to 1, 2, 3 and 4. And total number of edges, this is denoted by E. Here total number of edges is 1, 2, 3, 4, 5 and what? 6. So there are total 6 number of edges. So just put it here. So total number of edges is 6. Now in a planar graph, you can see that with these lines, with this line bounds, your graph is actually divide the whole plane into some sub regions. or the subsections, and these are called actually the regions. So generally a plane representation of a graph divides the plane, this total plane, into some windows or into some faces, different faces, and these are called actually the regions. So here this is the first region, you can see that this is the R1 first region, and it is actually created by this triangle. This is the second region R2, this is the third region R3, and the total outer portion is another region which is R4. Okay, so that's why there are basically four types of region. So we generally denote this region by R. So number of total region, this is denoted by R, and here R is equal to 4.
Resume the end of the plane that is
Okay,
bound by pieces.
so someone have already actually, I think, unmute your mic. So just mute your mic. Okay, Nishu, please mute your mic. Okay, so basically this is the region. So region means the portions of your graph which is created by these lines. So this is called the region, and here your total graph is actually divided into four regions, and we denoted this region by the R1, R2, R3 and R4. So basically if you take only one edges, so now tell me how many regions are created there?
Sir, 2.
How it is two? Can you
One
separate this?
region, sir.
Can you separate these two regions? Obviously, there is one region, because this is this portion, this outer portion, actually this is just one region. So that means to form two region, you list at least one cycle or circuit, na? At least one cycle or circuit, a closed work. At least you need that. So after that, there will be two regions, but otherwise there is always one region. So here you can see the only one region is there. If your graph is a null graph, that means only one vertices is there, V1 vertices is there, vertex. So then again there is also one region, and this is denoted by the R1, only one region. If it is a triangle, then number of region is equal to what? 2. R1 and another outside R2. So here the number of region is equal to 2. Region is equal to 2. And here number of region is equal to 1. Region is equal to 1. And here number of region, this is equal to again 1. Is it clear to everyone? Is it clear?
Yes, sir.
Now
Yes,
tell
sir.
me how many regions are there? Tell me. How many regions are there?
3.
3, sir.
3. So this is the first region, this is the second region, and this is the third region, the outsider portion. So total number of region is 3. And this number of region is denoted by R. And there is one popular theorem in your syllabus, very important theorem. And also the proof is important for the for your exam. That the only proof actually comes in your exam is this theorem, the Euler's theorem or the Euler's formula. And by this Euler formula, you can determine the region using the edges and the vertices. You can determine the vertices between from the edges and the regions. That means the Euler formula actually is a formula which connects the region, the number of edges and the number of vertices of a graph. So that means you will see one relation between this R, between this E and between this N in this Euler formula. Euler's formula. And it is very important formula, but you will actually feel little bit difficulties to understood this process. So that's why if you get any difficulties in understanding, or if you have any doubt, just stop me and ask, because this is a theorem of graph theory, and theorem of graph theory is not very much easy. So Euler formula actually says that a connected planar graph G, a connected, so connected graph means there is one walk, exist from any vertex to another vertex. So always you can walk from one vertex to another vertex through this graph. That means suppose this is one of the connected graph. So you can start from any vertex and you can go to any vertex by using some walk. So that's why it's a connected graph. But if we take another part here, then this graph is not a connected graph, because if this is the vertex V1 and it is V7, and if you want to go from V1 to V7, you can go by any of the road or any of the walk. It is impossible to travel from V1 to V7 because there is no edges which connect this portion and connect this portion. So that's why this is a disconnected graph, and in this disconnected graph, these connected portions, this is G1 and this is G2, these two are the connected portions and these are called the component. So in a disconnected graph, the connected portions of the graph is called the component of a graph. So these are all part of your previous syllabus, the semester 2 syllabus. So now we only focus on the connected concept. So connected means you can walk from one vertex to any other vertex. There is at least one connection to go from one vertex to another vertex. So this is called the connectedness. So a connected, now just take it. So a connected planar graph G with n vertices and e number of edges and R regions. Okay, take here for a connected planar graph G with n vertices, e number of edges and R regions, the formula n minus e plus R is equal to 2 holds. Always n minus e plus R is equal to 2 holds, or in the region form it will be R is equal to what? E minus n plus 2. These are two same. That if a graph have e number of edges, n number of vertices, then the number of regions in this planar graph is R is equal to e minus n plus 2. That means you can use this formula to determine or to check the previous number of regions in your graph. So R is equal to e minus n plus 2. This is your formula. So our formula is R is equal to e minus n plus 2. Now we use this formula to this graph. Now tell me, here number of vertices is 4, number of edges is 6 and the number of region is 4. Now we check that by using this formula. So by this formula R is equal to E, so E is equal to 6 minus N is equal to what? 4 and plus 2. Now you can see this is what? 4. Okay. Now comes to this. So here how many vertices are there? What is the N for this part, for this graph? What is the N?
2.
N is 2. What is the E? E is equal to number of edges 1. Now calculate R. So R is equal to E is equal to 1 minus N is equal to 2 and then plus what? 2. And you can see this is 1. So number of region is equal to 1. Similarly, for this null set, for this null graph, again you can see that here N is equal to 1. Here E is equal to no edges are there, so E is equal to 0 and R is equal to number of regions, so E is equal to 0 minus N is equal to 1 and plus 2, so that means it is 1. And similarly here there is N is equal to number of 3 vertices, E is equal to 3 number of edges and that means the number of region R is equal to 3 minus 3 plus 2, that is 2. So total number of region is equal to 2. So that means without determining from the graph, by using the vertices and the edges, you can determine the regions formed in a planar graph. And also if the regions are given and the vertices are given, you can also calculate the edges. So this actually connects the relation between this R, E and N. So that's why this is important. But now we want the proof of this theorem also, of this Euler formula. Now the question is how to prove that. So first of all, we take it as an induction process because we know how to prove it by using the induction method. So we start with R is equal to 1. Okay. So let R is equal to 1. So here R is equal to E minus N plus 2. So that means we start with R is equal to 1 and then we prove it for any values of R. That means if any number of edges are there, then we prove R also holds. So first with R is equal to 1. Now tell me, if R is equal to 1, that means only one region is there. That means, is there any circuit or not? This is a question. If R is equal to 1, that means the number
No.
of region is 1. Number of region is 1. So that means it should be simply a only null graph, or it should be of this type of line, or it should be some line of what? Pendant vertex, this type of graph, or this type of graph. Okay. So in this type of graph, you can see the total number of region is what? 1. So region will be increased if you actually create one cycle or one circuit. If you closed it, then actually one region is developed. That means if you connect these two lines, then there are two regions. One region is R1 and another region is the outside R2. But if there is no circuit and no cycles, then actually number of region will be 1. Is it clear? When number of region is 1, now this figure have a name, have a specific name in a graph. Is there anyone who can tell me what is the name of this graph? What is the name of the graph where no circuit or cycles are there? These are a special type of graph. These have a name. Yes. What is
So
the
no
name?
cycles, no, क्या बोले
No
सर? No cycles
cycle,
and no
no circuit. That means no closed walk is there, no closed path, no closed trail is
simple
there.
graph.
Now
Simple graph.
simple graph means the no self loop and no parallel edges. This is called the simple graph. These have a name, special name, that a graph where no cycle and no circuit occur. These are called tree. Okay. So these are called
Okay.
tree because in a tree you can see any of this type of cycle or circle because the tree branches are produced in this way always. These are the production of the tree branches. You can never see this type of branches in the tree. Did you see this type of branches in the tree? Is no, actually this is also one special type of graph where no cycles or the circuit occur. So that's why this is one of the example of tree. And for the tree there is one property and very famous or important property. The property is a tree of n vertices. A tree of n vertices have how many number of edges? Here the number of vertices is 1, 2, 3, 4, 5,
N
6,
minus
etc.
1.
N minus 1 edges. N minus 1 edges. Because if you take more than any at least one more edges, then you have to produce one cycle or circuit. Okay. And it contradicts that it is a tree. So that's why if it is a tree with n vertices, then it has n minus 1 number of edges. And we now use this concept for this f is equal to 1. So let r is equal to 1. then G has only the infinite region. Okay, if you have any doubt, just stop it here because it is very important and probably it comes to your exam and the proof is not very much easy. So if R is equal to 1, then G has only the infinite region, only one region, and it is the infinite region. So we can say that G cannot have any circuit, because if there is any circuit, then at least two regions are there, because a circuit bounds a region. So whenever a circuit bounds a region, that means you will not get one infinite region. So you will get one infinite region and another finite region. That means there are two numbers of regions here. So that's why we say, so G cannot have any circuit because a circuit bounds a region always. Now, so that means we can say that your G is a tree. Nah? We can say that G is a tree because there are no circuit, and since this G has n vertices, so it has n minus 1 number of edges. This is the property of the tree. That is, we can say that your E value is n minus 1. Number of edges is n minus 1. Now put all these values in this equation, that means R. So now E minus n plus 2, this value is equal to, place n minus 1 in place of E, minus n plus 2, that is, it is 1, and this is equal to the R. Okay. So here we can see that for this value is equal to n minus 1, your E minus n plus 2 is equal to R. That means it holds. So the theorem is true for, R is equal to 1. So for the R is equal to 1, the theorem is true. Now we have to take that theorem is true for R is equal to M, where M value is greater than 1. Na? M value is greater than 1. That means for any graph which have more than one number of edges, we take that this theorem also holds true for this graph. And after that we say, we will actually show that for one more vertices it also holds, one more regions it also holds. So let's start the next step of the induction method. So this is the next step of the induction method, and let R greater than what? 1. We take that.
सर
Let,
तो सर तो ऊपर कीजिए ना,
huh?
स्लाइड थोड़ा ऊपर कीजिए ना।
I will share this slide. Okay.
मैं वहाँ पे छूट गया, मतलब डायग्राम। हाँ, ओके।
Okay. If you have any doubt, okay, then you may ask. And if you want to take the snapshots or like this, then I will obviously share this slide.
बिकॉज सर ये जो हम लोग कर रहे हैं, वी आर यूजिंग मैथमेटिकल इंडक्शन, हमको लग रहा है
हाँ, yes,
प्रूव
it
करने
is
के लिए।
obviously लग नहीं रहा है. This is the mathematical induction process of proving that we start with R is equal to 1. We show that for R is equal
ये
to 1,
मुझे लगा
this
सर कोई दूसरा इंडक्शन होगा।
no, this theorem is true. Now we taking that, we are not actually taking M here because it makes the graph difficult. So that's why we take that, let R greater than 1. That means the theorem is true for any R and where R is greater than 1. So for R greater than 1, we take that, and the theorem is true. The theorem is true for all connected planar graph having less than R region, less than R regions. Now read it carefully. Now we say that we take that R greater than 1. That means R is not 1, R value is greater than 1. My number of regions is more than 1. And also by the induction method, we take that the theorem is true for all connected planar graph having less than R regions. यानी कि R region से छोटा कोई भी, यानी कि R-1 रीजियन का ग्राफ में, R-2 रीजियन का ग्राफ में ये वाला हमारा जो थ्योरम है ये होल्ड करता है. दैट मीन्स वी टेक दैट. तो हमने दिखाया R इज इक्वल टू 1 में ये होल्ड करता है. And then we take that not only R is equal to 1, R is equal to 2, R is equal to 3 and R minus 1 number of regions में hold करता है. And we now show that for R number of regions it is also holds. So that's why we take that let R greater than 1 and the theorem is true for all connected graph having less than R regions. That means having up to R minus 1, this theorem is true. We take that by using the induction method. Now we show that for R it also holds. Now the question is less than what should it as number of R regions. Okay. Now the question is that graph G, now since R greater than 1, since R value is greater than 1, is G a tree or not? Now is that G a tree? It is a tree.
No, sir. No, no.
Because now we take that region is greater than 1. There are more than one region. That means obviously one circuit will be there. Obviously, at least one circuit will be there, and it will actually make this graph that it is not a tree. So that's the problem. But we can only use this theorem for the tree. We can only use this theorem for the tree, but not for a general graph. So that's why since R greater than 1, we can say that G is not a tree. Not a tree. So what can we do now? That means, so G has at least one circuit. At least one circuit. Na? G has at least one circuit. Okay. And suppose this is our tree, but this time R value is greater than 1. So there may be more than one number of T. There may be 2 tree, maybe 3, more than one number of actually cycle or circuit. There may be 2 circuit, maybe 3 circuit. Because there are multiple number of regions now. And it is not a tree. So we can say that since R greater than 1, so G is not a tree. So G has at least one circuit, at least one, maybe more than that also. Now the question is, and let A be an edge, A be an edge of a circuit, So we take that, obviously, let this edge is A, or let this edge is A, let maybe that in a circuit, just take any one edge as A. Now, this G minus A graph is also a planar graph. Planar graph. Is it true? G minus A graph, it is a planar graph.
Yes, sir.
Okay. Now, suppose we are taking only one circuit. Now we actually increase the circuit. Suppose only one circuit is there. Now this is suppose G, and after that we remove this line A edge from this graph. Now this G minus A is also a planar graph because this G minus A, since this G minus A is actually a subset or proper subset of the subgraph of the graph G. Now due to removal of this edge A, now these two regions of this graph, this is the region 1 and this is the region 2, now combined into one region. Did you notice that? Okay. So now we are again taking this graph, just see it. So suppose this is your graph, that suppose this is your graph and this is your A. Now there are R1 and R2, two number of regions. Now you can see that by this edge A or by this circuit, there are two regions. But if you remove this A edge, that means in the G minus A, there is not that edge. So now your region is combined into one region. Is it correct? Is there any doubt? After removing this edge, now your graph is changes to a graph where regions are also reduced by one. Is it clear? Or once again I say that.
Yes, sir.
Actually, we have already taken that our theorem is true for r minus 1 number of edges. We already taken that. We have taken that. That let r greater than 1 and the theorem is true for all connected planar graph having less than r regions. That means we already taken that our theorem is true for 1, 2, 3 and up to what? R minus 1 number of regions. Now we show that it is also true for r. That means if we can reduce the region by 1, then we can use the previous formula for the induction. If we can reduce the number of region, so it is our aim that we want to reduce the regions by 1. So that means if in your actual graph there are, suppose so many connections are there, so many connections are there, so that means here you can see this R1, this is R2, this is R3, this is R4 and outside of this is R5. Now whenever you omit one edges from here, this A, suppose this is the edge and in the graph G there are 5 number of regions, but whenever you omit that A, these two regions will combine to form one region. These two regions will combine to form one region and it will produce that G minus A graph has a 4 number of regions. That means now you can apply your induction for this graph. Not for the G, but for the G minus A graph, you can use your previous formula because you already have taken that our formula holds for any graph which have less than R number of regions. Is it clear? Is it clear? Am I audible?
Yes, sir.
Okay. I can understand that it is difficult. But if you have any problem or queries, you may ask. But it is very important for exam.
So,
Yes.
can you repeat the last portion?
Yes. Dekho. So we have taken that first from where we start. We start that our theorem is true for r is equal to 1. We have checked that in this portion. That for r is equal to 1 in this portion from here to here, we have checked that our theorem is true for r is equal to 1. After that, we have checked that our theorem is true for any other values, that means up to 2, 3, 4 and up to what? R minus 1. Okay. And we show that our theorem is also true for R. That means now we are taking one graph which has R number of regions. And we have already taken that our theorem is a hold for R is equal to 1, 2, 3 and R minus 1. And now we start a graph with the region R. So suppose this is one graph and where R number of regions are there. R number of regions. That means suppose this is one arbitrary graph, just we are arbitrarily planning this graph just without intersecting the line because this is one of the planar graph and just intersect this line, and there are so many number of regions here and you can see so many number of regions are there. And Suppose now we are defining the region. This is R1, this is R2, this is R3, this is R4, R5, this is R6, R7, and this outer whole portions actually represent the R8 because there are no bounds other than that. So there are total 8 regions, and we are taking that there are so many extension also, and that means total number of R number of regions are there. R number of regions are there. Total. Now the question is, suppose we take any cycle. So since R is greater than 1, so that means it is not a tree and it contains at least one cycle, because if there is more than one region, so there is obviously one cycle, but otherwise you can draw your graph, because if there is one region, we already see that this is like a tree, and if there are more than one region, that means two region, then obviously there will be one cycle. Now take any one of the cycle from here, any one of the cycle. There are so many cycles, like this is one cycle, this is another cycle, this is another cycle. Take any one cycle and take any one edge between that. Suppose this is the edge, you take that as your edge, that edge. Now whenever you omit this edge from your graph, suppose you omit that, তো গুলো একসাথে কোথায় গেল, suppose okay, suppose this is the edge and suppose you omit that edge, that means now you can see after omitting the edge, your edge is reduced by what? E minus 1, because you omit one edges, and also these two regions are now combined to produce one region. Now there are not two regions, there are one region. That means your region is also reduced by 1. We have total R number of regions. Now in the new graph we have total R minus 1 number of regions. Now is it okay in the new graph?
Yes, sir.
So now we have already taken that our theorem is hold for the R minus 1 region. That means you can use the Euler's theorem for this R minus 1 number of regions graph. We can use that, and now we are using this theorem to prove the remaining. Just next line is where we left. So we left at the line that if R greater than 1, G is not a tree, so G has at least one circuit. Now let be an edge of a circuit. Now this G minus A is also a planar graph, and where due to removal of this graph, now due to the removal of an edge A, two regions of G will be combined, and so number of edges, number of regions of this new graph G minus A is what? R minus 1, and the number of edges of G minus A and the number of edges of this graph G minus A is what? E minus 1.
E minus 1.
Therefore, by our hypothesis, we get, for the graph G minus A, the previous theorem hold, and here this R minus 1, this is equal to what? E minus 1 minus n plus 2. Is it correct? Because for the new graph, R minus 1 is the region and E minus 1 is the edges, so we can use the previous theorem here. Now just omit this minus 1 and minus 1, and you will get R is equal to E minus n plus 2 again. And since by induction, and we can say that hence by induction, this result is true, is true for all the connected planar graph, for all the connected planar graph. So now just check the algorithm of this proof. So from where we start? So first we start with r is equal to 1. That means total number of region is 1. So total number of region is 1. That means only one infinite region is there. So no bounded region is there, and that means there is no circuit. And since there is no circuit, that means it is a tree. And in a tree, we know that if it has n vertices, then n minus 1 edges are there. So by using that, we have taken e is equal to n minus 1, and then we put these values in the expression, that e is equal to n minus 1 minus n plus 2, and it will be 1. And from where we start, that r is equal to 1. So you can see that this hypothesis is true for r is equal to 1. So first, like the induction process. So in the induction, we first prove or verify that this hypothesis is true for r is equal to 1. After that, we have taken that for any r which is greater than 1, we have taken r which is greater than 1, and we assume that for any values less than r, this hypothesis is true. That means this hypothesis is true for 1, 2, 3, 4, and up to r minus 1 number of regions. Now we will show that for any graph with r number of regions, this hypothesis is also true. Now since number of region is greater than 1, that means it have at least one cycle or circuit. It have at least one circuit, that means a closed path, at least one closed path here. Now suppose this is the closed path and A is an edge associated with the closed path or the circuit. Now if you remove this edge A, now your new graph which is produced, this is G minus A. Now this G minus A graph have r minus 1 region, because by removing one edges, also this region will combine and it will produce just one regions. So that means edges are reduced by 1 by just discarding the A, and also the region are also decreased by 1. So now your new E is E minus 1 and new R is R minus 1, and since the number of region are R minus 1, that means you can apply the previous hypothesis now, because this hypothesis is true for any number of regions less than R. So that's why we use the hypothesis with r minus 1 and e minus 1, and then you can see that again r is equal to e minus n plus 2. So by the hypothesis, by this induction method, we can say that this result is true for all connected planar graph, and this is very important theorem. Okay, now if you have any doubt or any queries, you can ask. If you understood it, it will be easier, but otherwise it is very difficult to write it in the exam. Is there any doubt?
No, sir.
No, sir.
So then we comes to another statement for the disconnected graph, but here the proof is not required. The only proof required in this chapter is that only one proof required, and it is your syllabus mentioned proof actually. So but otherwise you don't need any of the proof, just the statements are enough. So here the another statement, the same Euler's formula, for the disconnected graph, for the disconnected planar graph, like this type of graph. This is one of the disconnected planar graph, and you can see it is one of the disconnected planar graph. That means these are the component G1 and G2, and there is no connection between this. So if it is a G graph, so then this in this G graph there is no connection between this component and this component, but it is a planar graph, because you can make it in a plane, in a actually plane, and no intersection is also there. Now in this graph, the Euler's theorem also holds, but here you will get another new terms which is k. K is the number of component. K is the number of component. Component means here number of components are 2. That means the component means the connected number of connected graph in a disconnected graph. So in this disconnected graph, there are 2 connected graph. So that's why number of component is 2 here. Now the Euler's formula for this type of graph says that a disconnected planar graph G, a disconnected planar graph G with k components and n vertices and e number of edges determines R is equal to e minus n plus not 2 plus k plus 1 number of regions. So this is another term. In the previous, we have seen that R is equal to e minus n plus 2, but instead of 2, you will now see that k plus 1 term here. That means R is equal to e minus n plus k plus 1 number of regions. You can verify it by using this graph. Just no proof is needed, and just for the verification, you can see for this graph, what is the number of n here? What is the number of n? 1, 2, 3, 4, 5, 6, and 7. 7 number of vertices are there. What is the number of edges are there? E is equal to 1, 2, 3, 4, 5, 6, and 7. And what is the k? K is equal to 2. So now put all these values. So E is equal to 7, N is equal to 7, plus K is equal to 2 and plus 1. That means total 3 number of regions are there, and you can see the regions. This is R1 and this is R2, and total the outsider portions. These are the another regions. So here we have verified that this holds for the disconnected graph. Okay, and there are several usage of these two theorems, and also one corollary of this first theorem, and which is also important. Corollary means the deduction from the graph, and the corollary statement is that in a simple connected planar graph in any, this is one of the important, not theorem, this is just a corollary. So in any simple connected planar graph with R regions, N vertices, E edges, and where E is actually greater than 2, suppose E edges, and where E greater than 2, the following inequality inequalities must hold. Number 1, E greater than or equal to 3 by 2R, and number 2, E less than or equal to 3n minus 6. These two inequality always holds, that E greater than equal to 3 by 2R and E less than equal to 3n minus 6. Now tell me how to do that. Is there any ways? So from the Euler's theorem, we have this statement that E value, R value is equal to E minus n plus 2. This is the Euler's formula. We have. Now we have to prove that E greater than equal to 3 by 2R. Now tell me the way. Now, how many regions are there? R regions, na? So now tell me, to produce one region, how many edges are required? To produce one region, how many edges, minimum how many of edges are required?
0.
To produce a region, suppose only one, it will gives you one region. Okay. Now this is a one infinite region. So to produce one infinite region, you need at least one vertex. No edges are required. Okay. But to produce a bounded region, because you can see in your actually question or the in your statement, it is given that e greater than 2. So e greater than 2 means number starting from the 3 here, starting from the 3. So e is 3. So if e is 3, then you have only one number of infinite region. But since here this is a simple connected and planar graph with R regions, and where we can say that there is any bounded also. Okay, it will be better some simple connected graph if we also put the bounded concept here, or otherwise whatever may be. Now tell me, to produce one bounded regions, how many number of edges are required?
3, sir.
3. To produce one bounded regions, you need at least 3 number of edges. That means, suppose there are R number of total regions, R number of total bounded regions. So that means maximum number of edges there, or the minimum, suppose the total minimum number of edges are there is what? 3 up. Suppose R number of total bounded regions are there. That means there will be total, so with R, take it as bounded regions or bounded regions and n vertices. So to produce this R number of regions, is it okay that 3 are values? So there are total R number of regions. That means to produce one region, we need at least 3 edges. So to produce this R number of edges, so minimum you will need that 3R number of total edges there. And also every one edge is attached to two regions, na? R1 and R2. Whenever you take one edge, now you can see that it actually belongs to two number of regions. That means one edge contributes to two number of regions. So if you want to generate R number of regions, that means you will require at least 2e, this total number of edges, to produce that, at least 2e number. That means your edges number should be greater than or equal to these values, because e is the total number of edges and one edges is connected with two regions. So that means it will produce one regions here and another regions here. So if we just calculate the total number of edges by the regions, if we relate that, so here it is the region numbers and it is the edge relation with the region number, and where it is the edge number and it is the region relation. So two number of regions attached with one edge and one number of region is attached with three edges. Is this statement clear? Two regions are attached with one edges. This is R1, this is suppose R2. So two regions are attached with one edges and one region is attached with how many number of edges? 3. And there may be some edges which does not produces any regions. Maybe there may be some edges which does not produces any regions, only contribute to one region. So that means this number of edges is always greater than that. So this left hand side portion is always greater than the right hand portion. Now tell me, is it clear? Why the left hand side greater than the right hand side? Because suppose if you have this type of graph, then you can see these are producing some regions, but there are so many edges are there which are not contributing to these regions. These numbers, these edges are not contributing to the regions. Only regions are formed by this number R1, R2 and R3. That means to form this region, you will need at least 1, 2, 3, 4, 5, 6 and 7 number of edges. So that means to produce one, you need 3, and to produce these 3 regions, you need at least total 3, 3, 3, total number of 9 maximum, if they are also connected in this way. If they are connected in this way, then you can see that the maximum number of requirement is 1, 2, 3, here 1, 2, 3 and here 1, 2, 3. So total 9 number of edges are required to form these 3 edges, and from these 3, and the other edges, other subsidiary edges are all contributing to the only one regions, and here one regions, and there may be more than one number of edges, and maybe many number of edges and contributing to form just the infinite regions. So that means this left hand side portion, this 2e, is always greater than or equal to 3 of r. So from these relations you can directly get that e greater than equal to 3 by 2r relations. If you have any doubt, you may ask your questions. Is there any doubt? Otherwise we will state the proof. I can listen anyone. Am I audible?
Yes.
So just you have to write that, not so much thing. So since each region is bounded, since each region is bounded by at least 3 edges except the infinite, because it has infinite number of edges and there is no bound, and each edge belongs to exactly 2 regions, that is 2e. So 2 is the region relation, that 2 number of regions is attached with 1 number of edges is equal to, and this number is greater than, this edge number is always greater than equal to 3 numbers of edges are required to form 1, that means the 1r, 1 regions. So that's why this 2e greater than or equal to 3r, because in your figure you may see this type of also in the planar graph, that here to form 1 regions you have 1, 2, 3 number of edges, but these regions, to connect that, to form this outer region, there are 1, 2, 3, 4, 5 and 6 number of edges. It actually contributes to find the outer regions. To contribute the outer, to produce the outer region, at least 3 is needed, always at least 3 is needed, because if it is not a null graph, since this is e greater than 2, that means E start from 3. So that means your graph is either that or that, okay, or more than this type of graph. Now you can see, to finite the infinite region, the outer region, always there are 3 edges. To find the infinite region, always there are 3 edges. And here also, to find the infinite region, there are 1, 2, 3, 4, 5, and 6 number of edges. So to find one region, you need at least 3 number of edges, and every edges are actually attached to two number of regions, exactly 2 number of regions. So here the edge numbers may be greater than the number of regions, total edges required to the number of regions. So that's why 2e is always greater than or equal to 3 of r. And to form that relation, you will directly get that e is greater than equal to 3 by 2 of r, and it is your first proof. Now for the second proof, just use the direct Euler's formula and you will get that r is equal to e minus n plus 2. R is equal to e minus n plus 2. Now from here you can calculate the value of e. So this e value is equal to, or you can also put the r values here directly in this equation. Now put r is equal to r value in that equation, you will get e minus n plus 2. This value is greater than or equal to, not that, we have to put r value. So e greater than equal to 3 by 2 into e minus n plus 2. So that means 2e greater than equal to 3 minus 3 of n and plus 6. So if you take it in the left hand side, you will get e less than or equal to 3n minus what? 6. And this is the second corollary proof. So that is the first corollary and this is the second corollary. So this is one of the theoretical class. So that's why it will actually seems a little bit boring. But from the next class, we will start the application of these properties. There will be only application of these properties. First, the application of Euler graph, and also for the disconnected graph and the connected graph, and then these two corollary. And these two corollary are very efficient to prove the non-planarity of a graph. That if it not holds, then your graph is a non-planar graph, and you can see that. Just suppose for the K5 graph, the number of vertices is 5, number of edges are 10, you can see that. And now if you use these values to this relation, now you can see that e is equal to what? E is equal to 10. This is less than equal to 3 into 5, n value 5, and minus what? 6. That means 10 less than equal to 15 minus 6 equal to 9. Is it correct? Is it correct?
Yes.
So,
Is it correct? No. 10 less than equal to
no.
9. How is it is possible? So that
Sir,
means,
no. Sir.
for the K5 graph, this relation will not hold. You can see that. Because K5 is not a planar graph. That's why this corollary can prove the non-planarity of your graph without drawing the graph. So that's why it is important. Next class topic will be some example, more example, or more problems from these theorems, and after that the duality concept. Okay, so I think it's enough for today.